So welcome to the Physics Colloquium. Today we are very grateful to have our own Jim Gates, who is going to give us talk about a problem which was quite old, which he and his students was able to solve in supersymmetry. And of course, Jim doesn't need any introduction to this audience, but it's traditional that we still say a few words. And Jim has received his bachelor's in physics and mathematics from MIT in 1973, and 4 years later, he wrote first MIT thesis on supersymmetry. So that was his thesis topic, and he basically started to teach as a TA being at MIT, and this year is actually 51 years since he started teaching in the classroom, so quite impressive, more than half a century. So Jim taught at MIT, he taught at the University of Maryland, Caltech, a few other places, and since a few years ago he is professor at Brown and the director of the Center for Theoretical Physics, BTPC. And also, as I'm sure all of you know, Jim is currently serving as APS president, and he has a number of various awards, which I wouldn't list, but we are very happy to have Jim to talk about supersymmetry. Please.
Thank you, Greg. And I'm told that it's. Thank you, Greg. And I'm told that the speaker's allowed to take off their mask. I was just talking with Antal, and it's a little bit weird now to see people in real life, because for so long, you know, there's this little screen, and you see your friends, your students, your colleagues, and it's all on the screen, and then all of a sudden they're there, and you're like, wow. That wasn't just the television program I was watching. There's a real person behind that face. So I'm feeling very happy to be out in the world again and giving talks. So today I wanted to talk about something that basically started when I came here at Brown. The foundation actually goes back like 15 years, maybe earlier. But I've been able to prove to my colleagues that I'm not chasing my tail. There was a meeting, an APS meeting, maybe 5 to 7 years ago, where this is in an article you can read, where whoever wrote the article said, in the audience, one physicist was heard to say, either Jim Gates is a genius or he's chasing his tail. And so I think I've been able to prove that I don't think I'm a genius, but I don't chase my tail either. And the work that I've done here at Brown has actually been, as I said, a validation of a point of view that I've been arguing about for some years. So let's get started. So we're going to do a lightning fast sort of fly through talking about subjects that are not theoretical physics, but also subjects that mostly physicists don't think about. So there are some problems in my field, in my part of physics, that are decades old that have not been solved. And they're all around issues of supergravity and string theory and what have you. And so in 2004 or so, I decided the following, that these problems, which are hard, haven't had solutions in like 2, 3, or 4 decades long time. And that convinced me that when some of the smartest physicists in the world can't solve a problem, the problem is the point of view they're bringing. That is what's called the framing of a question. Now, for physicists, the simplest example of this is if you have a problem where there is spherical symmetry, then circle coordinates are probably the best way to try to solve the problem. You don't try to do this in rectangular coordinates. And so no matter how smart some individual is, if you have a problem in rectangular that naturally has circle symmetry, the worst thing in the world is for a group of people to try to use rectilinear coordinates. And so my point of view about what has held up my field, my part of the discipline, was that people had fallen into the rut of trying to think that you can always use the equivalent of rectangular coordinates. And today I'm going to tell you about how you can get away from that paradigm and find information that's never been found before. So one thing that happened to me as I reflect back on it, is that I start thinking about supersymmetry in a different way, in a way that involves graphs, networks, and polytopes. So let's see what that means. So first of all, genetics. As you all know, Watson and Crick actually taught us that the fundamental bit of genetic material that guarantees legacy inheritance is this double strand of DNA. And it turns out that physicists, I think it was Bohr, had actually postulated that maybe there's some sort of crystal on which that kind of information was posited, and that's how we have inheritability. Well, he was not quite right about a crystal, but there's certainly a polytopic crystal-like structure that's responsible for that. And in the last decade or so, or 2 decades now, the field of genomics has come in fully into play, namely that we have so much information about genomes now that you can construct computer databases. And what I'm showing you here is the front end of a database for the basic, let's see, what is it? Basic local alignment search tool, BLAST. And what it does is if you can find some genetic material and just a snippet, say at a crime scene, for example, if you can actually send that information about that, you sequence it and get the usual data, you can send it to this particular website, and it will analyze the complete genome from which that snippet comes. So we're learning to, and so it's a matching problem. In fact, you can think of it as a giant jigsaw puzzle. You have this one little piece, and you want to know where it fits in the big puzzle. So I started thinking about this kind of technology, and could it help me solve the kind of problems that I was interested in? This is another view of the BLAST webpage. The other thing about, the other way that networks are useful in biological sciences related to genomes is actually following the way that evolution works. So this is a set of graphs that I got from a friend by the name of Rick Lansky. You can see his name at the bottom of the transparency. And what Rick was doing was actually asking an extraordinarily interesting question. In evolution, it has long been a question about if you could restart the clock on evolution, would the resulting endpoint be what we have today? And so he's actually run some experiments with E. coli. And what he found is that the answer is almost always yes, but not always yes. That there's a small probability that you're going to wind up in a different place. And in some ways, what's really interesting about the work that he's done is it reminds people like me of path integrals and quantum mechanics. Because remember, the way quantum mechanics works in the Dirac-Feynman view is that you have this space of histories, and that you sum over all histories to figure out the probability of our universe. And so you can see this, this sort of alternative viewpoint about what evolution is as something like quantum mechanics. And this is a particular graph from some experiments that Rick and his group published in Nature, where they definitively showed that you almost always get the same endpoint, but not exactly always. There are small probabilities for divergences. You see polytopic structures in crystallography. All of us have heard about Bragg scattering when we were undergraduates and graduate students. And so this, let me just point out that this is one mineral, class of minerals called phagocytes. And the real reason I'm interested in this, you'll see at the end of it, but it's a crystalline structure, and if you ask for a typical member of this family of crystals, it turns out the structure you see is something called the truncated octahedron. It's mostly, as you can see, aluminum, and my vision is so bad these days, silicon. Thank you. And they're arranged in this crystalline. This is the basic unit cell of it, and it's like I said, called a truncated octahedron. Now you can go to Wikipedia if you want to, like I tell my students. Now what has just happened to Jesus? Yeah, that's actually my assistant, Mary Sutton. Can you hear me, Mary? Yeah, I guess not. She doesn't seem to smile. I have no idea why Mary's popping in like that. Some of my graduate students recognize that face. So while a technical wizard will make sure that Mary isn't on our screen, let me continue. So you can go to Wikipedia, like I often tell my students. Wikipedia is actually quite remarkable in terms of in terms of the accuracy of the mathematical and scientific stuff that you can find there. A lot of students in high school are told don't use the Wikipedia to help do your homework because you're going to find answers that are not reliable. But that's just not true in the stuff we do, because the people who basically scrub Wikipedia are very persistent and accurate in the information they put there. So here's that same crystal that I told you about. It's a truncated octahedron. This is the way that mathematicians would look at a perfect view of the crystal. You can, for example, you can see that where is it? I don't see the information here now, but you can see, for example, opening angles, number of vertices, number of edges, and so let me highlight those two numbers. There are just 36 edges and 24 vertices. And so now let me jump into supersymmetry. Now, one thing I feel obligated these days to do is whenever I give a talk on supersymmetry, I have to point out it is not dead. Because my colleagues like, Rick and Greg and Mina actually go out in the real world and they query nature about whether these crazy mathematical ideas are realized. And so, as I said, I feel these days obligated to tell you why people like me continue to search for supersymmetry. In fact, it's not just me. Even bona fide particle phenomenologists and accelerator physicists are still looking. So first of all, what is supersymmetry? Well, for that, the first thing I can tell you is let me start with the standard model. Standard model is a description of all the elementary particles that apparently we need to make our universe. You can see here the electron and its spin. You can think of this as having separated the electron into its spin up and spin down states. And we have the muon, the tau particle. Muon looks just like an electron, but it's 200 times more massive. Tau particle looks just like an electron, but it's 1,700 times more massive. In addition to the leptons, so they're the neutral leptons, the neutrinos. In addition, you have quarks, up, down, charged, strange, top end, bottom quarks. This is you. These are the particles that make up matter. Now, you're not just a soup of particles, you have a very definite shape, and that's because there are forces that hold these parts in definite shapes. And they have a set of forces, particles that carry the forces from matter particle to matter particle. So here we have the most familiar of those force carriers, the photon, which is actually the carrier of the electromagnetic force. There are 8 of these objects called gluons. They are the force carriers between the quarks. Then we have the Z and plus and minus W bosons. They're the force carriers for the weak nuclear force. And then finally in 212, we discovered that the mathematics around how these objects get their mass is through a process called spontaneous symmetry breaking. And that process solves a problem, namely it tells you how to relativistically describe a massive spin 1 particle, but the price that you pay is you have to also say in nature there's another particle, and this other particle is the Higgs boson. And this was first predicted at the end of the 60s. And it's far more than Higgs, by the way. There's a whole group of people associated with the actual prediction, but Higgs is certainly one of them. That's supersymmetry, folks. Now, I'd like to represent the discussion in these 2 diagrams, because if you look at a lot of places for a standard model out of CERN, you see this diagram, they say, oh, these are particles standard model, then they introduce you to different generations, and then when someone comes and says supersymmetry, you wonder, well, how does that make it more symmetrical? And this is pretty obvious how it makes it more symmetrical. You can actually physically see the left-right symmetry that's there if these other particles exist. And that's in fact a way to understand why supersymmetry really is symmetrical with respect to standard modeling. You're establishing this left-right symmetry, namely a symmetry between the particles that are the matter fields, which are all fermions, and a set of matter fields that are all bosons. All of these are boson force carriers, and supersymmetry says you ought to have a set of fermion force carriers. And that's the simplest way I can explain to you what supersymmetry is. To run down some of the science, these are slides from about 2013 about some of the searches that were underway at CERN. They're all negative because people said, gee, we should find this result, we should find that result. this particular plot, this anomaly, and none of these have been fulfilled by the experiments as of 213. I first was reporting on Atlas. This is a list of 213 results from the CMS, and all of these things have actually been negative. And so a lot of people say supersymmetry must be dead. So I'd like to point out a couple of things. First of all, what's actually being tested at the LHC is not supersymmetry. It's a model. It's just like saying, it's just effectively like what's going on is Newton's law a model? No, it's a framing for models. You have to put inputs into Newton's second law in order to describe any physical system. And so what's going on right now in terms of the search for supersymmetry is that there's a model that people are probing called the minimal supersymmetric standard model, but it's even worse than that because what's actually being probed is something called the constrained supersymmetric minimal model. So what is that? Well, first of all, there are a bunch of extra parameters that come in when you say supersymmetry because all those particles I showed you, they have to have masses. Perhaps they mix with our particles. There are all kinds of things like that. And so when you go to this idea of more symmetry, the first thing it does is actually give you many more parameters than occur in the standard model. And so in order to get rid of that, what's actually happened is that people, phenomenologists, based on their best understanding of the physics of elementary particles, say, well, let's set a bunch of those parameters equal to one another. Now, it's their intuition guiding it, but who says their intuition is actually what nature does? And in fact, so what's being disproved are the assumptions that people have put into what supersymmetry ought to look like, as opposed to actually an unbiased query to nature herself, are you supersymmetric? So that's the problem that's going on. Now, unfortunately, I have to, from my perspective, I have to say we're kind of getting what we deserve because certainly when string theory sort of became very popular in the 90s, there was sort of there was kind of a cult that arose around the subject. People say, oh, string theory is going to solve the universe and we're going to find this unique theory and it's us. And even at the time, I disagreed with that. I gave a talk in Poland around 1987 or so, and I said that the belief that string theory would find a unique solution that's us is akin to the Aristotelian view of our solar system. We shouldn't think we're so special. And yet that's what was going on in the first round of trying to apply superstrings to the idea that we could find a description in the math that looks like our universe, and that we would be uniquely chosen by the mathematics. That's what people used to say. I thought it was naive then, and it's gotten much worse since then. So, to summarize, what's going on with phenomenological supersymmetry? This is a very an old cartoon about a guy who's searching for his quarter. A policeman sees him down on his knees. What are you searching for? Searching for my keys. The policeman asks him, where did you drop the keys? He says, far away from here. Why are you searching here? Because the lamplight is here. Right? And that's what's going on. That's literally what's going on when people talk about the demise of supersymmetry. They're searching where they think the keys are going to be, not necessarily where nature says they are. So I kind of anticipated this. In 2006, I wrote a paper in which I said a number of things. First of all, it was the first time that I publicly talked about the fact that if you believe in extra dimensions, then you've got a real problem. Because you see, if you think that our theory is described by some higher dimensional theory with hidden dimensions, then if you want to make contact with our physics, you have to put some extra assumptions in. These assumptions are called compactification. And in the initial round of superstring theory, which you can read about, for example, in Brian Greene's book on called The Elegant Universe, they talk about Calabi-Yau compactification. That's how we're going to find our world. Well, if you had been a superstring theorist at that time, you would have noticed something very interesting. Fairly quickly after the notion of Calabi-Yau completely intersecting Calabi-Yau manifolds, CICY is the acronym, you would have noticed that people found other compactification techniques. The first other one that I recall was something called an orbifold, which is a mathematical technique which is different from Calabi-Yau manifolds, and it produces other solutions that look like our world. Then there were Gepner models. Then later there were some things called the covariant lattices. This process of proposing more and more compactification techniques has gone on to this very day. And if you look at the models that people are studying these days, they use things like what they call non-geometrical compactification, G2 compactification, and every single one of these things is different apparently. And so this points to a problem. Namely, it's a problem that weirdly enough is philosophical. It says that if you have some kind of starting point, which is a higher dimension, and you want to connect with our universe, then you need a way to actually classify the number of ways you can connect to our universe. Now, this is a problem that Sheldon Glashow points out in the Elegant Universe video. He says, if a theory makes no predictions, then is it really a theory? And in some sense, at the time he made the statement, I wasn't in agreement with him. But after thinking about it some time, and this problem about not even being able to count the number of ways that you can get to our universe, no one has a science of compactification. At least I've never seen one. And as long as that's not true, then we can't even figure out the number of ways you might connect. And if you can't, that's a problem called ontology in philosophy. So higher dimensional, the idea that our universe is some kind of construct from an ab initio higher dimensional mathematical space has this ontological problem at its very foundation that people have ignored for decades, but that doesn't make the problem go away. It's still there. So in this paper, I talked about those two things. I also pointed out that it was to my mind, it was highly unlikely that the LHC would discover supersymmetry. This is in 2006, before the LHC turned on. This paper, as you can see from the cover, was published in Physics Today. I'm sorry, is there some way to get the lights down in here so that this might be a little bit more? Thank you. So this might be a little bit more legible. Thank you, Greg.
Make it a little brighter.
No, that's good. That's actually good. Okay, so in the article I said, even if nature is kind enough, it might be a century before we had direct observation of a superpartner, contrary to what a lot of people thought. And in fact, I also commented that it would be much more likely that evidence for supersymmetry will come from precision experiments, not from direct production. Direct production, by the way, is what we saw with the Higgs boson. It's a direct production of the Higgs boson and watching subsequent decays. Namely, you actually, as an intermediate state, you've actually created the particle that you're looking for. But precision measurements actually do something slightly different than that. You don't look for direct production. What you do is you look for the influence of these particles you think are out there on the physics of the particles in our world. And one of the ways that you can do that, and so in the end I said it's going to be like Mark Twain, where he didn't actually make this quote, but people often say Mark Twain made the comment that the rumors of my death are greatly exaggerated. That's not actually true, but it's often said that way. And I thought SUSY would probably go that route. So in 2012, after the first scientific run was unsuccessful, the British Journal Physics World asked me my opinion before the second scientific run. Did I think it was even likely that we would see it there? I again told them I thought unlikely. So where are we going to see supersymmetry? If you force me to make a bet, I'm going to say something like the superpartners are probably around 30 to maybe double that number, TeV. And that's well beyond the reach of the LHC. And so that's why I thought we probably would not see them. And I was willing to make a bet when very few physicists were willing to make the statement that the LHCs probably would not see superpartners. So in 2012, I repeated this analysis, and let me just show you this tree. If you were looking, this is a giant sequoia. If you were here on the East Coast looking for this tree, you'd never find it, because it's only on the West Coast. And that, again, I implore people, that's what's going on in our physics. We're searching with the best of our technology, but there's a whole energy continent out there that we can't get to. And so the question about demise of supersymmetry is premature at best. Why am I sure supersymmetry is there? Well, it has nothing to do with dark energy or naturalness or any of the reasons that you read about in the literature. I think supersymmetry will likely be there in the end because it has something to do with the stability of the quantum vacuum. Now, what that actually means is if you know something about quantum field theory, you can have what's called a false vacuum. And if you're in a false vacuum, then there's a probability that you'll decay to the true vacuum. If that occurs in our universe, we'll disappear because the Higgs boson would lose its mass. None of the laws of physics that we know would be here. And the worst thing about a spontaneous creation of the true vacuum is that we wouldn't see it coming because it travels at the speed of light. The first we would know is when we get here, and then we'd be gone. We still wouldn't know it. So if we live in a universe that is in a metastable state, and there's some evidence that this might be the case, some of my more esteemed phenomenological colleagues might recall that if you look at the ratio of the masses of the top quark and the Higgs boson, by some analysis, that's a metastable state. So if we're in a metastable state as a universe, you're going to need something to stabilize us, and that's where I think supersymmetry would have to play a role. So anyhow, that's my spiel about supersymmetry. So if you're going to do precision, which is what I suggested, then you have to think about precision measurements. One of the greatest examples of that is the measure of G-2 for both the so-called G factor for the electron. But more recently, what we have been informed by our colleagues who've been studying the muon is that they seem to find some anomalies in the G value for the muon particle. And this is precisely the kind of place I thought you would first see the evidence for supersymmetry, in an anomaly of something having to do with standard model particles, not by direct production. Now, is this a sign of supersymmetry? No, because this is right now, I believe, a 4 sigma effect. And at least in particle physics, the standard for discovery is 6 sigma. And so all we can say is that we don't really know yet. But if this signal keeps growing in size in terms of its standard deviation, then something is going to be there. And then eventually we're going to be faced as a civilization, as a species, to try to figure out what that something would be. So this is how I always thought supersymmetry would be discovered, by precision experiments. What do these experiments do? Well, this is a Feynman graph. This is a Feynman graph that shows you how the law of electrical repulsion works between electrons. You have 2 electrons here and here. They travel along. They send a signal from one to the other. That signal carrier is the photon. That photon says there's another electron close by. You need to be repelled. So that's classical physics. However, quantum physics says the process could be more complicated. So these are Feynman diagrams, illustrated Feynman diagrams. And so here we have an electron that will emit a particle of light at this point, that it later reabsorbs, and then sends a second photon with the message to get away from me. So that's one possible process called a vertex correction. For those of you who study quantum field theory, you'll learn how to calculate those things, because that's the kind of torture they do when you're a graduate student. There's another correction called vacuum polarization, where you have the first electron emits a photon, which then disintegrates into its particle-antiparticle pair. Here we're illustrating that by an electron and the positron. They have opposite charges. They get back together. E equals mc squared says all their mass gets converted back into energy in the form of a second photon, which then is the end message carrier in this process. And again, it's a lot of fun learning how to calculate these things, but it's something only young people have the strength to learn to do. Because when you get old like me, you're probably not going to want to do this. But we all go through it once in my business. So these are the kinds of things that would hint at supersymmetry. Because instead of having an electron-positron pair here, you might have a superpartner and its anti-superpartner that would be in this intermediate process. And so these anomalies that people are watching in G-2 are, to me, the first true signs that something else is there, and that it might be supersymmetry. It could be something else, but it might be supersymmetry. Okay, so now I'm taking you through my spiel about why people like me don't lose sleep at night when journalists call them up and say, "Isn't supersymmetry dead?" People who know what's going on understand where we are, what has happened, and why there's some challenges out there. I'm not going to take you through some mathematics associated with the Standard Model. So the Standard Model has a bunch of gauge groups, groups that are represented by matrices, and in particular we have actually we have SU3, which is the color gauge group for the force carriers that keep the quarks bound in the interior of hadronic matter. That's what we call color dynamics. But SU3 was initially discovered not by looking at color dynamics, but looking at flavor dynamics, and observed that there were 3 generations of quark, up, down, and strange quarks. And you look at the mathematical trends. If you think of a wave function where those 3 particles are the basis of the wave function, then you have to look at 3 by 3 transformations, and that's where the SU3 comes from. So Gell-Monn and Okubo, I believe it was. I'm sorry, Gell-Monn and Neyman, back in the early 60s, actually formulated this idea of a wave function that had these matrices to generate symmetries, just like rotations generate symmetries. So I'm going to start with SU3 because I want to teach you something about polytopes. So you start with these matrices, you can calculate the commutator, you find this set of objects closes on itself. If you do the anti-commutator, you get something slightly more complicated, but I don't need that for this talk. These matrices are the generators of transformations. Here's the closure. We put a factor of a half in because that's sort of a physics tradition. These are the non-vanishing structure constants. But the really cool thing about SU3 is that 2 of the 8 matrices can always be found to commute with each other. And so what you can do is take those 2 commuting objects, look for their eigenvectors and the eigenvalues, and then you have suddenly a new space. In this new space, the eigenvalues are the coordinate of this new space. So it's not physical space, it's a space where the eigenvalues of the commuting generators constitute the basis vectors. So now the rest of the generators, remember there are 8, I only took 2 of them to find this space. The rest of the generators actually act like things that generate motions along a crystal. And so we combine the rest of them into what's called I spin, U spin, and V spin in the old days. And the other thing, so why doesn't I talked to you a moment ago about the fact that if you believe in extra higher dimensions, there's an ontological problem. Namely, you have to then classify all possible compactification techniques. Why is that not true of the standard model? The answer turns out to be because the mathematics of the standard model is understood well enough, and principally by the mathematician Cartan, that we know every single possible group that you could ever write that's mathematically consistent. And what that means is that you can denumerate every possibility of a gauge theory. So that's why there's not this ontological problem when you write the general gauge theory, because you know how to count them basically. Where it is there in string theory, well, it is there in any theory where you say higher dimensions, because you then have to be able to count the way these get to our world. And so this is part of Cartan's work that was also elaborated upon by Weil. And so we know how to count all these gauge groups, and that's what saves us from the ontological problem. But the thing that's really interesting about SU3 is I told you those other 6 generators act like motions acting on the coordinates in the space of eigenvalues. So let's look at that picture a little bit more carefully. I'm going to talk about isospin in the usual sense. These are what are called isospin raising and lower operators by the blue axis. This is I spin, this is V spin, that's U spin. And once you understand that these other matrices generate motions, you come up with the idea that there's a crystal of some sort where the particles that we think about are at the vertices of these crystals. And the other 8 matrices are actually moving us in these in this crystal. So here's the crystal. This is the crystal that sits behind SU3. And every single compact group that you can write down has the equivalent of this crystal behind it. And again, that solves our ontological problem. So what are things like quarks? Well, quarks are collections of vertices in this picture. So I've shown you here the picture of the quarks and their antiquarks. You take collections of these things, and there are rules about how to take these collections. So here they are in their standard representation, our up quark, our down quark, and our strange quark. Here are the antiquarks. You can get this pattern is allowed by the rules. And so the real question is, what are the rules for building representations on the lattice? And this is the octet, which is in fact the object that contains the proton and neutron in hadron physics. There's another octet that contains the pions, but both those octets, in terms of the eigenvalues, look essentially the same. And then there's this decouplet, which is in fact why particle physicists in the early 60s finally understood that we have to understand group theory. It was an observation by Murray Gell-Monn, a very famous experiment where this vertex here is something called the omega, and he predicted it on the basis of the structure of everything else there at a conference in CERN, right after these two particles have been discovered. And this is what it looks like in terms of particle language. Okay, so I've tried to convince you that the standard model actually has these hidden mathematical crystals that sit behind the structure of it. And so the question is, I also told you there's this idea about supersymmetry. So the question is, are there these kinds of crystals for supersymmetry? That's the problem I am pursuing, and that I have been pursuing quite vigorously since I've come here to Brown. What are these crystals? What are their structures? What are the rules for constructing them? And what information can we get from them about the structure of supersymmetry that people don't know how to answer? So I'm going to first give you an example of big success that I had with my students who are sitting in the audience here. Let's see, I don't see Hazel, but she's here somewhere. Oh, there. So Miss Hazel Mock and my other student, Miss Young-Greg Hugh. When I first came here to Brown, I taught a course in group theory along with Anto. Anto was kind enough to let me have a couple of lectures in his group theory course. And so I was invited to speak about supersymmetry. And so I don't know how, I can't remember the number of lectures it was 3, 5, whatever it was. But some students got very interested in that. And one of them was Hazel. So she was my first graduate student here at Brown. And then the next year, Young-Greg came along. And so we've been studying, the entire time I've been here, I've been looking at the structure of these crystals that no one had actually ever seen before. In fact, it's not even clear how to get them. That's one of the things that's really mysterious. And so I want to explain to you the process of how we get to these crystals and then what we understand about the way, the rules for constructing them. So let me ask you to solve a quantum mechanical problem. Here's a harmonic oscillator illustrated here. And we know there are a set of energy levels. And if you're thinking about putting particles in these energy levels, which is what the typical hydrogen atom problem is, you know that particles at a fermion have the property that no two of them can occupy the same state. So that's a problem that's well solved. Anyone who's completed a course in quantum mechanics can do that. And there's a transition just to touch on physics. So now I want you to imagine a quantum mechanical system that has 32 energy levels. 4,294,967,264 degrees of freedom. That includes spin, and whose ground state, that has a ground state configuration. It turns out that that's the problem that I was able to solve with Hazel and Young-Greg. It's a problem like saying, what's the ground state of a certain kind of quantum mechanical system? And I want to talk about that a little bit. It's actually the all-shell structure of 11-dimensional supergravity. So if you study supersymmetry, read a lot of books, you'll learn about these things called superfields. And this is a typical structure of a superfield. It's got some kind of field variable, and then there are these theta things. You do Taylor series expansions. And then the coefficients of this Taylor series, those are the fields that you actually do physics with. Now, one thing that's really interesting about these kinds of superfields is that they can take particles of different spins. So this is actually spin 0, this is spin 1/2, that's spin 0, that's spin 0. That's actually spin 1, spin 1/2, and spin 0. So whatever these things superfields are, they gather together fields of different spins that we know from physics prior to supersymmetry. And so what I've written you here is the way it works for 4 dimensions. And if you count the number of degrees of freedom, you say, aha, 4 plus 4 is 8. So there are 8 fermionic degrees of freedom and 8 bosonic degrees of freedom. So that counting was pretty simple. So the problem that I had been worried about, which apparently, I don't know why it doesn't bother other people, is that for over 40 years, we didn't know how to do this. And yet this was the most advanced technology of talking about superfields. Why is this important? Well, let me take you through one theory. It turns out that if you put a vector index on that collection, instead of a photon, you get a graviton. And so this is how superspace packages together gravitons and gravitinos. And these other things here, well, there are gauges where they're not there. It's just like in a gauge theory. Some of the field variables, like in, if you think about electromagnetism, the photon has four degrees of freedom, but one of them is removed because gauge transformations get rid of that 1 degree of freedom. So it's effectively only 3 until you actually go on shell, and then it becomes 2. So in the same kind of way, there are lots of these extraneous degrees of freedom that we never understood how to get rid of. And you can get rid of them by fixing a gauge that's equivalent to Coulomb gauge, and you get to a smaller set of objects. And it turns out that this smaller set of objects is still consistent with the Dirac-Fermi path integral, Dirac-Feynman path integral. If you go fully on shell, you only keep the propagating degrees of freedom, and this turns out not to be consistent with the Dirac-Fermi, Dirac-Feynman path integral. And that's something that bothers me. So I'm trying to figure out, can we do better? This is true for the photon. The same sorts of thing happens. It turns out 11-dimensional supergravity, as discovered, is relatively simple to theory to write. There's a graviton, there's a 3-form, and there's a gravitino. But it's on shell. That means that all these extra degrees of freedom that are consistent with Dirac-Feynman path integrals aren't there. And nobody knew how to find them. That's the weird thing about the problem. So we're going to try to find them. And that's where we're going to get this 4,294,967,000 bosonic and fermion degrees of freedom. We solved this problem. It took us about a year. But the way that we solved it is we totally threw away the idea of a superfield. In fact, we went back to the ideas that there are these polytopes that actually govern the behavior, just like the matrices have polytopes that describe their behavior. And so we concentrated on the polytopes, and what we were able to do was discover all the rules for making these polytopes. And when you do that, you can actually reconstruct the things that would come out of this superfield notion. These polytopes always have this characteristic diamond shape. They start narrow at one end, they go up to a maximum length, which is here 16, which is illustrated here, and then what's up here is the flipped image of what's down there. So we actually solved the problem. We could tell you about all the spins that are in this object that no one had ever been able to denumerate before. And we could tell you the number of fields, because even that was not known before our work, that there are 1,198 boson fields and 1,186 fermions. You say, well, wait a minute, the counting doesn't work. Well, it turns out that if you include the Lorentz representations, it all works out. How do we do this? I'm going to talk about that later, but basic idea is that you write, no person could do this. You have to take advantage of information technology techniques. And so we basically write codes that study these crystals and tell us what the answers are. And these are just the listing of some of those answers I'm showing you. So that was, as I said, to me, that was a big moment that I'm grateful to having come here to Brown, because I'm not sure how much longer it would have taken me to get to that stage. But I can now point to something that we can do with these polytopic methods that nobody else in the world can do this right now. So this is a unique Brown capability to be able to actually look at these higher dimensional superfields and see the spin content completely. So let's get back to the polytope part of it. So how did we do this? Well, back in 2004, I was working with a physicist named Michael Fox, and what we figured is that a theory like supergravity you can think about as being the apex of a pyramid, and that perhaps there is some kind of a shadow that is cast, and by studying the mathematics of the shadow, you would then get insight back here. And I've now proven this by the fact that we can now look at 11-dimensional superfields based on the techniques that we learned in one-dimensional quantum mechanics. So how do you do it? Well, the first thing you have to realize is that field theory is really about looking at the forward light cone. And so we couldn't solve that problem, but we can solve quantum mechanics. So we, instead of trying to solve field theory in the forward light cone, we actually only solve it along a line that's in the forward direction. I'm going to speed up a little bit because I'm running short of time. So how does it actually work? I'm going to, like I said, speed up here. So here's the field theory description of some of these superfields. And they're connected by various transformations. And when you do this process of projecting down to only time, what you find out is that these superfield transformation laws can be described by these symbols here. Just like Feynman rules describe calculations in covariant quantum field theory. So these symbols are networks. And so our guess and bet was, let me study the properties of these networks, and I bet I can figure out stuff about things in higher dimensions. So you get these networks, and they have, like I said, I'm a little bit short of time, so I have to speed up. They have a number of properties, isomorphisms. Here's the field theory language that most people who know something about supersymmetry would use. For us, instead, we study these. When you write these networks, the curious thing that happens is that all the complication of the higher dimensional problem gets replaced by a set of matrices. And at some level, that's expected, because if you look at how supersymmetry works, people often don't know the answers, and then they go out and do calculations. But these calculations for unknown constants are always linear calculations. That means that there's some kind of a linear algebra problem that contains the answer that they're looking for. And what we're trying to do is find what that problem is. So it turns out that you can start with standard approaches and then get down to these sort of smaller objects. You find this set of matrices. These matrices are the adjacency matrices for networks. And again, you have to know something about network theory, but the way that people talk about networks is often through adjacency matrices. So it turned out that for 4 dimensions, that thing I call V is really telling you about the structure of a 4-dimensional hypercube called the tesseract. Again, speeding up. So these L matrices and R matrices have a peculiar form. They are permutation matrices times factors that are square to the identity and are diagonal, which we call these Boolean factors. Every single matrix in a supersymmetrical theory has that structure, in the minimal theories. Here's some examples. And so the question is, how does a one-dimensional theory know to tell the difference between what was going on in 4 dimensions and what goes on in 1 dimension? Because it's kind of mysterious. And so when you actually look at these matrices, you discover that they involve permutations of 4 objects. That's what this is a notation for permutations. So again, speeding up. So here are the permutations. This is the identity map. This says 1 goes to 1, 2 goes to 2, 3 goes to 3, and 4 goes to 4. This map here says 1 goes to 2, 2 goes to 1, 3 goes to 4, 3 goes to 3, and 4 goes to 4. So this object that you're seeing here is a listing of all possible permutations of 4 objects. But you'll notice that there are links that connect them in a very peculiar way. My student, Alexander Chianchara, was a person who brought the attention my attention to this sort of thing. And when I looked at it, I knew that this is exactly what I needed to be able to tell the difference between a 4-dimensional theory reduced from a vector multiplet, a gravity multiplet, or a gauge multiplet. Because what happens is, let me go back. Notice what's jumping out there. Where did we see those 2 numbers before? Fauger-sites, right? Yeah. So somehow that crystal that I pointed out in Fauger-sites is hiding in the mathematics of supersymmetry. That's what we discovered. And the way that it occurs is that the supermultiplet that describes the quarks and squarks, I'm illustrating those in green lighted here. The supermultiplet that describes the photon and the photino is here. And so what happens is, under this projection process, the higher dimensional theory projects the permutations in 1 dimension, but it's different permutations. And so the identity of the higher dimensional multiplet is encoded to where you are in this object, by the way, is known as a permutahedron to the mathematicians. And so it's telling you, in higher dimensions, I'm a scalar multiplet with quarks and squarks, or I'm a vector multiplet with photons and photinos. And so it is the kind of thing that is analogous to the eigenvalues. But I haven't actually shown you the eigenvalues yet. So let me get to that, and that'll be the end of our talk. For those of you who know something about crystallography, remember this raising and lowering operator stuff? So now I'm going to show you raising and lowering operators in the context of the eigenvalues associated with these crystals of supersymmetry. So here's that object again. And what's really weird here is that here are the permutations. You can see them all listed as nodes. But these things in greens are also permutations. They're a special subclass of the permutations. And so what you can do is you can ask the question, what occurs in a supermultiplet? So there, for example, is the chiral multiplet. And like I said, I'm going to speed here because I'm short of time. So I told you, I took these 4 special operators, the identity, the red, green, and blue links. There were 24 states. And so the question is, are there composite operators that connect these states in such a way that they're the flashing, blinking lights that you saw in the permuhedron? For a crystallographer, these kinds of operators are called hopping operators. They move from one vertex on a lattice to another operator. And so the question is, what are the hopping operators for all those supermultiplet projections? Turns out, it's pretty easy to figure out. And every single one of those supermultiplets have the identical set of hopping operators. And the hopping operators are, in supersymmetry, what the raising and lowering operators are in SU2 and SU3. So this is the crystal that sits behind minimal supersymmetric representations. And I'm showing you the hopping operators here, here, and here. Those black links are the hopping operators. That means that we know what raising and lowering in this system looks like, just like you know what raising and lowering is in SU2 and SU3. So there's one hopping operator that was just 2 links. There's another hopping operator that has 4 links. And then the final hopping operator has 6 links. So now we've begun to get the kind of feeling that you have in SU3 about how you move around the basic lattice. So how many quadrilaterals do you see in this image? Six. How do you? So the next question becomes, yeah, there's 6. So how do you teach some piece of artificial intelligence to identify that? So this is a problem that we undertook last summer in my summer program, because I do research with undergrads during the summer. And it turns out that you can do it in a set of objects that we call correlators. You see, if I start with this object, which is in one kind of multiplet, its hopping operator takes me to here, so I can ask how many steps did it take to get there, and it's 2 links. I could also count this 1, 2, 3, 4, because this thing is also in the same multiplet, so that's a 4-link hopping operator. And the final operator is 1, 2, 3, 4, 5, 6, because that's the other operator in the multiplet. And so what you have to do is teach the computer how to see this. And the way that we did it is by calculate what we call correlators, which is basically, if you give me a particular vertex, how many links does it take to get to any other vertex in the entire permutahedron? And it turns out those are calculations that you can do. And it turns out that it's the eigenvalues that tell you. It's the eigenvalues of these correlator matrices. Now this is like a computer vision problem. Now I don't actually know much about computer vision, but I would be surprised if someone who works in computer vision hasn't figured out that when you look at an image, if you can define vertices and edges, and therefore define the distances between any particular vertex and any other vertex in the image, I would be surprised if someone hasn't figured out that if you look at the eigenvalues of those matrices, that's how you do it. That's the simplest way that I and my students worked out for this last summer. So we learn from people who do computer vision. So I'm now at the end of my talk. So what are we going to do next? Well, there's this thing called the Hexipenti Runcicated Truncated 7 Simplex, because that's the next object that's a crystal that's relevant to supersymmetry. Here, n equal 2 supersymmetry. Now, we have a long way to go, because actually, at the end of the day, if we're going to get back to 11 dimensions, you actually need n equal 8 supersymmetry. So we're slowly building up our competencies in understanding its mathematics about how these crystals are related to M theory. And at the end of the day, we hope to be able to produce a more complete picture of M theory than has ever existed. So that's what it looks like. That's this thing when you look at it, it's just a blob, right? So we're studying this thing. And let me just point out that I like to work with students. So last summer I worked with one of our master's degree students, Renee Kirk. And on this particular paper, you can see Yangre was one of my co-authors, and my graduate student, Alexander. Now, these are some other students I've worked with in 2021. And so I actually get students involved in all this research about looking at Hopking operators and these higher dimensional crystals and how they sit behind supersymmetry. And then, of course, I have to pay great tribute to Hazel and Yangre, because they were the folks who gave me the boost to follow this crazy vision I have that there are these crystals that sit inside of supersymmetry. We now know how to identify them, and we hope to be able to present as complete a picture of supersymmetry as is known for the standard model in terms of these crystalline-like structures that sit behind the representations. So these are the papers where we worked out some details for you. Thank you.
Thanks a lot, Jim. Now we have time for questions. Let's start with Zoom. Yes,
You have some Zoom questions?
we'll see. If you have a question, please unmute and just shout. In the room?
Anton.
Very nice. You started out with this analogy with genomics and this work of Lansky. Actually, what is the parallel? Where do you...
So the parallel, which I did because of rush of time, is the following. When you start with an on-shell theory, which is what we know for most supersymmetrical theories, like 11 dimensions, it turns out that's like having a snippet of the entire crystal in which the object exists. And so that's where the analogy is, that we can now, for the first time, if you give me an on-shell representation, I can tell you which possible crystals it fits in, and that then limits my efforts to basically find more information. So that's the analogy. It's like having the supersymmetric analog of the BLAST website that I showed you, and that's why I included it.
Any other questions?
There's a hand back there.
Thanks, Greg. Jim, am I turned on?
Yeah.
Why did that next crystal explode to such a large... that doesn't look promising for...
But we have faith in our students. So the reason is something I flew past because I was getting short on time, but let me go back to it. Thank you for the question, Jim. These crystals have exponential growth associated with them. You see, so in our world, if you wanted to write the Dirac equation, the Dirac wave function has 4 components. If you were in a 6-dimensional world, the Dirac equation would have 8 components. And so what you get is that the size of the spinner associated with the dimension in which you're working is what determines the dimension in which this crystal exists. And as you can see, let me put this in visual so you can see it. And as you can see here, you have exponential growth. And so that's why the thing explodes the way that you saw, and going from the Bermudahedron of 4 colors, which was relatively simple to write and show you, to the Bermudahedron in 8 colors, which is the next one relevant to supersymmetry, that just looks like this blob. However, like I said, we have confidence in our students.
Hi, Jim. Thanks for that nice talk.
Thank you.
My question is, it seems that nature realizes all the symmetries available to it. There's a quantum magnet in condensed matter physics that realizes the group E8, for instance. What would it mean if 100 years from now, after searching for supersymmetry, we still don't find it, and we conclude, our descendants conclude that it doesn't exist? What would it mean for nature that it didn't realize that symmetry?
Well, as I said, I alluded to my biggest concern, which is the stability against the false vacuum. Because I haven't done the calculations, but I'm pretty sure that if you look at vacuum tunneling, take two different theories. One theory without supersymmetry, and then look at the closest theory that has the same basic structure. Because as you know, if I start with a theory without supersymmetry, it could be just bosons, but if I have to have supersymmetry, I have to have... So take this one theory that is not supersymmetric, and then look for the closest theory that contains your first theory, but has extra particles. Like I said, I haven't done the calculations, but I have a very strong suspicion that if you look at tunneling in those two theories, that the supersymmetry will suppress the tunneling. And so my claim is that if it is true that the argument about the masses of the Higgs boson versus the top quark means that we are in a metastable universe, I would be worried about living in that universe without supersymmetry.
Thanks.
Any other questions? I actually have one question on this very point. So, I mean, vacuum stability, of course, is a very important issue, but all you need is to make the tunneling probability so that it doesn't happen in 10 to the 10 years.
Right.
And that's not a very hard thing to do because everything is exponentially suppressed. So we might disappear in the next moment, right? And
that's true. That's true. And but like I said, to me, supersymmetry, I've never thought supersymmetry was connected to the things that people say. It's very convenient that maybe it gives us a dark matter particle, right, that we kind of need for cosmology and astrophysics, and maybe it's there for the stability of the Higgs boson, because people were making naturalness arguments for decades about why the Higgs boson's mass is stable against the renormalizations that are necessary. Those things are all true, but somehow to me they never had a ring of being essential.
But gauge unification is, right? You show.
I think gauge unification is, yeah.
So you only need one miracle of stability.
Well, possibly so. But if nature's willing to give me more miracles like my existence, I'm going to take them.
Very good. Well, let's thank Jim again for this fantastic talk.
Thank you.
Thank you very much.
Yeah. Yep. Are you?
I got stiff.
Yeah. That happens to me all the time.
Yeah, this happens to me lately. Nice talk. Right?
Well, thank you, Antal. As I said, thank you.